So in your book, these two results are now in the theorem 1.51 and 1.52. And it says, if A is a matrix, can be any matrix m by n, doesn't have to be square, then an elementary row operation, one of the three we have, on A is given by a matrix multiplication E times A, where E, also E stands for elementary, where E is one of these elementary matrices. And now what we also learned, even better, E inverse, that means E is invertible, is also an elementary matrix. And there are three different types. No? There's the multiplication matrix type, the interchanging or switching type, and the addition type. So there's three different types of elementary row operation matrices. I just call them elementary matrices, but they're called elementary row operation matrices. Okay, so this in some way is really good. Also we understand now Gauss algorithm much better because we know whenever we do one step in the Gauss algorithm, we multiply the matrix from the left. Okay. And now is the time to put everything together. So we start with a linear equation system. We know we can write it as A times X equal to B. No? A is your coefficient matrix. X is the vector of your variables x1 to xn. And B is your right-hand side vector, the constants in your equation. Now we use Gauss-Jordan algorithm for the augmented matrix. So until now, what we do is we make the augmented matrix. We make A slash B. So this is our augmented matrix. We might hear the coefficients, make a slash or something to indicate this is our right-hand side. And then we apply the Gauss algorithm. No? We change rows, we add rows to each other, or we multiply by rows, for example, to generate leading ones. So we apply our Gauss algorithm. And where do we end up? We end up, after a lot of steps, sometimes at a reduced row echelon form. And then we stop. And this is actually, until now, this is after a while you understand how this works. If the matrix is not too big, you can do it. But it's kind of also everyone might do something else. No? Also, it's not like every student does the same. You might do something else than your neighboring student. It's not clear how you go there. But at the end, you end up with a reduced row echelon form. And now I like to write down how this row echelon form works. And now I like to assume that all the leading ones are on the left side, just to make my picture simpler, which essentially means I have reordered my columns. So here we have a certain number of ones. So these are the leading ones, otherwise 0. Then we have a block which we actually don't know what's in there. And the number of ones I like to call R. And then here on the bottom, if there is a bottom, is all 0. And then we have the right-hand side, where I have a changed right-hand side B tilde, and down here I have a changed right-hand side B star. And I don't really know what's there. It might be all zero, I don't know. So this is how the reduced row echelon has to look at the end. And just to make really sure what I mean by this matrix here, okay, sorry, I like to call A tilde. So A tilde is a reduced row echelon form only from the A part. And on the other side, I have the B part. Yeah, also is this clear what I mean by this? So you write the augmented matrix, run your Gauss algorithm, and you end up with something like this. No? So there are a bunch of leading ones. There's sometimes a block here. If the leading ones don't go all the way to the end, there's some numbers which I don't know. On the bottom, we have the zeros. And on the right-hand side, we have our modified right-hand side. Is this okay to everyone?
Yes.
Okay.
Yeah.
So now, with all what we did before, we know the Gauss-Jordan algorithm. Imagine this matrix is large, 500 times 500. Then there may be 20, 30, 100,000 of operations here. And you have no clue what's really happening. But now we know whatever is happening, it's a sequence of matrix multiplications, because now we know the Gauss algorithm is nothing else than a sequence of elementary row operations, and each of them is given by a multiplication with an elementary matrix. So from A to A tilde, I come by doing a number of steps of elementary row operations. So, okay, I move this up here. So for a moment, we still see this. So I start with the matrix A. I start multiplying with the first elementary row operation, then with the second one, and I don't really know how many there are. What I use the number k. K can be really giant number. It is often a very giant number. And at the end, we come out at A tilde. And A tilde is in reduced row echelon form. And we have R1s. So this is what we can, now we can say, this is actually what Gauss does, or Gauss-Jordan. We do a bunch of operations, and we end up with a reduced row echelon form. Okay, before I move on, I like to go back to the previous slide and say, so maybe just here, AX equal to B is solvable if, what is the condition that we actually find a solution here? It depends on the right-hand side, no? Here are only zeros, so if B star still has one leading one, if the one leading one is here on the side of the right-hand side, that's what we learned, I think, on Tuesday, then it's not solvable. So it is solvable if and only if B star is equal to 0. No? And it is uniquely solvable if R is equal to N, if the ones go all the way, so we don't have this block, because remember, for every non-leading one variable, we get a parameter. And it's only uniquely solvable only if we have no parameter, which means this guy must disappear. So it is uniquely solvable if and only if R is equal to N. Remember, we have here N variables. So I should have said something like A. Let's assume it's square. A is N by N. So sorry, I should have said this before, that N is my size of my matrix. So if R goes if the ones go all the way down to the bottom, then there is no parameter. And if R is smaller than n, we have at least one parameter, means if it's solvable, we have infinitely many. No? Okay, so I should have said this maybe earlier. So this is just here a remark. Once you're here, you can really understand what's happening. Okay, so now we go back to here. So our Gauss algorithm multiplies A very often with elementary operations to get A tilde, and A tilde has this shape. Now we can actually also move all the E's on the other side and isolate A. So for example, I can multiply by EK inverse from the left, then EK inverse is identity, so it disappears here and appears here. And I can do this one after the other with each matrix up to E1 inverse. No? I multiply from the left. Then these will all disappear because whenever they come together, they give me identity. So I have A is equal to E1 inverse, E2 inverse, up to EK inverse times A tilde. And what did we learn? Each of them, the inverse of an elementary row operation matrix is again an elementary row operation. So we can say again E1 inverse up to EK inverse are elementary, row operation matrices. And we know each of these guys is invertible. Yeah? Okay, and I like to call this equation here, okay, maybe I can later point to this, so that you have A multiplied by a row operation is E tilde. So let's call this guy here equation number star. And then the other way around, I have A tilde, elementary row operation, I get A. So I like to call this guy here equation plus. So later on, I like to go back to these. So now, like I said, now suddenly everything comes together, what we learned. What can we say if A tilde is invertible? If A tilde is invertible and I multiply by invertible matrices, what did we learn yesterday? Whenever you have two invertible matrices and you multiply them, the result is invertible. So in the moment you multiply one invertible matrix after the other with an invertible matrix, then A is invertible. That follows from this equation. One invertible, another invertible, and so on, because we know all these guys are invertible anyway, then A is invertible. Now we look at equation star. If A is invertible, these are invertible, then A tilde is invertible. Okay, so this is already a very important part. So the Gauss algorithm transports your matrix A to reduced row echelon form. And now it turns out, if we like to know if a matrix has an inverse, we only need to understand if the reduced row echelon has an inverse. And so this is the important connection we have now. I would like to go later back in the next result to these two equations. So we will see them again. But essentially, these two equations are now the foundation of our first really important result in our class here now. So, and this result in your book is called theorem 1.53. First, I write it down, and then we go over how do these things now all match up. And so 1.53 is something which is really, I would say that's the first deeper result in our class, which is not so obvious. And it really emphasizes, again, the importance of the Gauss algorithm. So let's do this.